Hello everyone, this is lecture 9 of course PE 500. In this lecture, we are going to cover the stability analysis and go through multiple examples to understand the different techniques behind stability analysis and the meaning of each. So let's begin by the definition of the stability. So stability refers to the ability of the system to return to its equilibrium state after being disturbed. And it's a cornerstone for understanding and predicting the long-term behavior of dynamic systems in bioengineering. And stability here matters in bioengineering and in our field because biological systems are inherently nonlinear and often operate near critical thresholds, such as gene regulation and neural firing. Also, stability analysis helps determine whether a system will settle into a steady state, oscillate, or exhibit a chaotic behavior. And also, if you are dealing with designing control systems, predicting disease progression, and optimizing synthetic biological circuits, we need to study the stability of these systems. There are three types of stability. The first is local stability, and here we are getting the behavior near the equilibrium point. Global stability, and here we are getting the behavior across the entire phase space. And asymptotic stability, where the system not only remains near the equilibrium but converges to it over time. And we will discuss three ways or three tools for stability analysis. The first is linear stability analysis, where we are going to examine small perturbations around equilibrium points using linear approximations, Lyapunov functions, and here we are providing a mathematical framework to prove stability without solving equations explicitly. Basin of attraction, and here we are going to identify the region in phase space where trajectories converge to a stable equilibrium. There are two challenges in nonlinear systems. The first is nonlinearities can lead to complex behaviors such as bifurcations, chaos, and multi-stability. Stability analysis must account for these phenomena to ensure robust predictions. As noted, the first technique is called linear stability analysis. And this technique examines the behavior of a system near equilibrium points by simply linearizing the governing differential equations, as it assumes small perturbations around the equilibrium and determines whether these perturbations grow or decay. Grow means instability and decay means stability. So the first step in the linear stability analysis is to identify equilibrium points by solving the system equations x bar equals f of x to find the equilibrium points where f of x equals 0. So simply we are going to get the points where f of x equals 0, and this will be our equilibrium points. Then we are going to compute the Jacobian matrix by evaluating the partial derivatives of f of x at each equilibrium point to form the Jacobian matrix J. Then we are going to analyze the eigenvalues of the Jacobian. If all eigenvalues have negative real parts, then means stable equilibrium. If any eigenvalue has a positive real part, this means unstable equilibrium. And if eigenvalues are purely imaginary, this means that further analysis is needed, or we can say neutral stability. So simply get the equilibrium points, solve the Jacobian matrix and get the eigenvalues, check each eigenvalue and make a conclusion. For the second step, we require to calculate and compute the Jacobian matrix. It depends on if you have one or two dimensional systems or more. So simply Jacobian evaluates the partial derivatives. So we need partial derivatives according to each variable. To understand the Jacobian and how to fill the Jacobian matrix, simply let's assume that we have two equations for a two-dimensional system. The first equation is dx by dt, and the second equation is dy by dt. So simply for the Jacobian matrix, we are going to put the first equation in the first row, a second equation for the second row, and if you have multiple equations, you will make multiple rows. And for each row, you are going to apply partial derivatives according to each variable. So let's say this is variable x and this is variable y. And if you have three equations, then you will have three rows and three variables, x, y, and z, for example. So how to fill the Jacobian matrix? So simply, we are dealing with dx by dt equation here and here. And here we are dealing with the second row, which is dy by dt, dy by dt. So simply, you are going to apply partial derivative to that one according to dx, and for that one according to dy, and for that one again, for that variable it will be dx, and for that variable it will be partial y. So simply put each equation in each row, and for each variable apply partial derivative. So here we're applying partial derivative according to x, and here for the second variable y. But for one-dimensional system, you will only get one row and one variable, so you will obtain dx by dt, which will be your equation only. As noted earlier, we are using stability analysis, especially linear stability analysis, in multiple applications such as gene regularity networks, where we are going to determine whether a gene expression level is stable under perturbations. Neural dynamics, where we are going to predict whether a neuron will fire or remain at rest based on the input stimuli. Population modeling, where we are assessing whether populations will stabilize, collapse, or oscillate. And for this technique, linear stability analysis, there are three limitations. It only provides local insights near equilibrium points, and it fails to capture global behavior such as limit cycles, chaos, or multi-stability. And it assumes small perturbations which may not hold for large deviations in nonlinear systems. With all that said, let's start with an example to understand how to apply the linear stability analysis. In this example, it says, the logistic growth model describes population dynamics where the growth rate decreases as the population approaches a carrying capacity K, and we will use this equation. dx by dt equals Rx multiplied by 1 minus x over K, where x is the population size, R is an intrinsic growth rate, and K is the carrying capacity. As mentioned, we have three steps. The first step is to find the equilibrium points by setting this equation, or dx by dt equals 0, and solve the equation to find the equilibrium points. So we will set this equation to 0 and start to solve it. So our aim is to find the values that can make this equation equal 0. So we may say that R may equal 0, and this is wrong because we are focusing here on our variables, and also R is a constant. As mentioned, refers to the intrinsic growth rate. So we'll focus on what are the values for our variables that will make this equation equal 0. So we may say that x can be 0. So there's the first assumption. Or this part can be 0. So simply at this time, 1 minus x over k equals 0. Then x, by solving it, will equal k. So we now have two assumptions, or two equilibrium points, x at 0 and x at k. When you find x or your variables equal 0, we can say it's trivial equilibrium, and otherwise it will be non-trivial equilibrium. So what is the difference between trivial and non-trivial? A trivial equilibrium occurs when all dependent variables, let's say x, y, and z, are 0, such as x equals 0. And the biological meaning behind that means it can be extinction, or no activity, or no production, or nothingness, and it helps to determine whether a system can sustain itself or not. On the other hand, non-trivial equilibrium occurs when one or more dependent variables are non-zero, and these equilibria represent meaningful non-extant states of the system. And here we are getting any value other than 0 for one or more dependent variables, and the biological meaning can be steady-state activity, or survival, or regulation. And here it provides insights into how the system operates under normal conditions. And both types of equilibria can be stable or unstable, depending on the parameters. Also, they can be crucial for understanding system dynamics, stability, and bifurcations. So in short, when you find that all dependent variables are 0, then you can say this solution is trivial equilibria, and otherwise it will be non-trivial equilibrium. The next step is to apply linearization using the Jacobian, and we have here one equation with one variable, so we are going to apply partial fraction according to that equation and that variable. So there's dx by dt, apply partial fraction according to x, the single variable in our example here, and try to solve it and simplify. So apply partial fraction here. So simply R is a constant multiplied by 2 parts. So apply derivative to the first part, which will be 1, and keep the second one. Plus, keep the constant, keep x, and apply derivative to this factor, which will be minus 1 over k. Try to simplify. R multiplied by 1 will be R multiplied by this factor will be here, Rx multiplied by this factor will be here. As you see, these two factors are same with the same sign, so it will be R multiplied by 1 minus 2x over k. So this will be our equation, or the result of the Jacobian matrix. Now, we need to evaluate f of x at each equilibrium point. So simply, this can be done using substitution. At the first point, which will be the trivial equilibrium, x equals 0, substitute, you will gain that this factor will be 0, so R multiplied by 1 will be R. R is a positive constant, so it will be more than 0. So at this point, the equilibrium point is unstable. As mentioned, if it's more than 0, then it's unstable. Less than 0, it's stable. And if it's equal 0, we can say it's neutral stable. A second point is k. Substitute, so it will be 2k over k. This will cancel each other. 1 minus 2 will be minus 1 multiplied by r will be negative r. So negative r is below 0. So at this point, we have a stable equilibrium. So now, x near 0 is a trivial equilibrium and unstable. X near k is non-trivial equilibrium and stable. This means that any perturbations around x equals 0 will decay over time, and the population will stabilize at the carrying capacity, which is k. But if you substitute it with 0, this means at this point or around this point, it will not decay and may not stabilize. Let's go to a second example for nonlinear dynamics, reflecting the Hill equation that models the gene regulation. As equation says, dg by dt equals beta multiplied by g power n over k power n plus g power n minus gamma multiplied by g, where g is the concentration of the gene product, beta is maximum production rate, k is half maximal effective concentration, or we can say activation threshold, n is the Hill coefficient, and it measures how sharply the gene responds. Gamma is the degradation or dilution rate. The first step, as mentioned, takes the equation, equal it to 0, and find the points. So, when you equal it to 0, you can move that part to the right-hand side to be like that, and then multiply by the denominator for both sides, assuming that g doesn't equal 0. So, it will be like that. Combine all of them together. Gamma g, kn will be here. Gamma g, gn, which will be gamma gn plus 1, and this part will be on the right-hand side. Move this part to the left-hand side to be like that. Factor out g, so it will be g multiplied by that whole factor. Now we have 2 points or 2 assumptions. Let's assume that g equals 0 or the second factor will equal 0. Let's say for now n equals 1 and solve it. You will find that g equals to that factor. Based on these 2 assumptions, we have 2 equilibrium points. G near 0, which is called trivial equilibrium, and this factor is called non-trivial equilibrium. Next, apply linearization. We have a single equation with a single variable. Let's apply the second step, linearize around each equilibrium point. So we have this equation, apply partial fraction according to g, and for simplicity for now, let's assume that n equals 1. So this part will be the denominator squared, the numerator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator. And for this part, the derivative of it will be negative gamma. Combine all of that together will be like that. Simplify. This will cancel that, negative and the positive. So the remaining will be this equation. Now evaluate this equation according to each equilibrium point. Near 0, substitute. You will get g here equals 0. So it will be k beta over k squared. K over k squared will be 1 over k. So it will be beta over k minus gamma. So if this factor is larger than this factor, then the result will be positive. And here it will be unstable. And otherwise, if this factor is below this factor, then it will be negative, and in this case it will be stable. A second, we have that factor or that equilibrium point. substitute in the equation. So the equilibrium point will be here to replace G. Now, again, you can simplify, and if the point or the result is more than 0, then it's unstable, and otherwise it will be stable. So using linear stability analysis, the steps are simple. Find the equilibrium points, find the Jacobian matrix, and this means linearization. Evaluate each equilibrium point, and based on each equilibrium point, you can decide if it's stable or unstable. So the key takeaway for the linear stability analysis is it's a powerful tool for understanding local behavior, but must be complemented with other techniques such as the Lyapunov functions for a complete picture of the system dynamics. The second technique is Lyapunov functions, and here we are using a scalar function v of x that we are going to suggest, and it provides a mathematical tool to prove the stability of an equilibrium point without solving the differential equations explicitly. And here it acts as an energy-like function where the system behavior can be analyzed by observing how v of x changes over time. Again, v of x will be assumed, as we are going to see in our examples, and we are going to analyze the behavior or how v of x changes with changing the time. It has two key properties. First, positive definiteness and non-increasing derivative. Here we must ensure that v of x is above 0 for all of x that not equal x of 0, where x0 is the equilibrium point, and v of x naught, the value should be equal 0. A second is that the derivative of that function should be below or equal to 0, and here v of x will not increase along trajectories. And if v of x is below 0 but doesn't equal to 0, then we can say this equilibrium point is asymptotically stable. Based on the properties and the assumption of our function, we can say we have a stability criteria using Lyapunov functions. First, we have Lyapunov stability, and this happens if v of x is above 0 for all points other than x naught, and v dash of x is below than or equal 0, and the equilibrium point here is x naught. And if you find that, then it will be called Lyapunov stability. Here, when you find something is above 0, v of x above 0, this is called positive definite. And if you find something like that with below than or equal, then you can say it's semi-definite. And if it's negative, then you will say negative semi-definite. So definite or semi-definite depends on if it's equal 0 or not. If it's equal 0, it's semi-definite, and if not equal 0, it's definite. Positive or negative depends on if it's higher or lower than 0. And Lyapunov stability ensures that the system doesn't diverge from the equilibrium point, and the trajectories remain bounded near that equilibrium point, but may not necessarily converge to it. Asymptotic stability is similar to Lyapunov stability, but here positive and negative should be definite. So here it's below than or equal 0, here it's only below 0. So we can say it's negative definite for the derivative and the positive definite for v of x. And here, if the derivative is strictly negative, it implies that v of x decreases over time, and this forces the system trajectories to converge to the equilibrium point. Global stability, if v of x is above 0, which is called positive definite for all points, and v of x bar is below 0, negative definite, and also v of x tends to infinity as the absolute value of x equals infinity. And we are going to understand how to capture whether it's Lyapunov stability or asymptotic stability during our examples. But for now, let's know which is below 0 or which is higher than 0, and which is semi-definite or definite, which is positive and negative. Again, Lyapunov functions can be injected in many applications such as gene regularity networks, neural dynamics, and population models. Also, Lyapunov functions has two challenges. The first is finding a suitable v of x can be difficult, especially for high-dimensional or highly nonlinear systems, and it often requires creativity and domain-specific knowledge of the system being modeled to predict or suggest v of x. To understand that, how Lyapunov functions work, and how to determine if the system is stable or unstable, let's consider this linear system. d of x over dt equals negative x. And you may wonder, do these techniques apply to linear and nonlinear systems? Yes. You can check the stability of any system, whether it's linear or nonlinear, following the required steps for each technique. So let's back to our example. We want to analyze the stability of the equilibrium point x around 0 using a Lyapunov function. Again, how to determine the equilibrium point? Simply take the function, equal it to x, and find the equilibrium points, as we did earlier. So dx by dt equals 0, so negative x will be 0. Here, x will be 0, as you see here. So the first step for the Lyapunov is to propose a candidate Lyapunov function. And a common choice for a Lyapunov function is a positive definite quadratic function. Let's say 1 over 2 multiplied by x squared. And we are going to use something like that, because when you are going to get the derivative of v of x, it should be x. So you are selecting some factors here to cancel each other after the derivative. Again, we have some conditions for that function v of x. It should be positive definite and above 0 for all points other than the equilibrium point. So the equilibrium point was 0. So here, other than 0, it's positive definite. So the first condition is achieved. The next step is to compute the time derivative of v of x. And here, by getting the time derivative, we need the derivative of x according to the derivative of the time. So to get that, simply, we will apply the derivative of the function according to x, and we have dx by dt, which is given to that equation. So to find dv by dt, this will cancel each other. So simply, this one will be the partial of v according to partial of x, and we have this equation which is negative x. Take the partial derivative here. As mentioned, it will be x multiplied by negative x, so it will be negative x squared. Now we have the time derivative of v of x. Now let's analyze as a step 3. It's positive or negative. At all points, it will be negative or 0, because if you inject here positive or negative, the result will be positive multiplied by negative, so the final result will be negative. So it's for sure negative. And is it semi-definite or not? If you substitute by 0, then it will be 0. So at this case, v bar, or the derivative of the time derivative here, is below than or equal 0 at all points. So we can say that Lyapunov stability is achieved also, because two conditions are reported: positive definite for v of x and semi-definite and negative for v bar of x. And we can say also that it's asymptotically stable if we ignored the equilibrium point. If you ignore that equilibrium point, then the equal sign here will be ignored. So the symptotic stability will be reported also. So the system achieves Lyapunov stability and asymptotic stability. By all means, the system is stable at this equilibrium point. Let's go to a second example to deepen our understanding. In this example, we have a nonlinear system. As mentioned, the stability techniques apply for linear and nonlinear systems. Here we want to analyze the stability of the equilibrium point near 0 and near plus and minus 1 using the Lyapunov function. Again, we determine that the equilibrium points are these points when we got that function and made it equal 0. As you see here, factor out x, you will find x and x squared minus 1. Here we get x equals 0, and from here we get x equals plus minus 1. Now, the first step in the Lyapunov function is to propose a candidate. Let's assume the same candidate as we did with the previous example, 0.5 x squared. The next is to compute the time derivative of v of x. As mentioned, we will apply derivative according to x to this function and multiply it to our function here. The derivative of it will be x. Multiplied by the given function will get negative x squared plus x raised to the power of 4. Factor out x squared, so it will be x squared multiplied by x squared minus 1. And we did this step for simplicity, as we are going to see now. Next, we need to analyze v bar of x. We have the points 0, 1, and negative 1. So at 0, this result will be 0, this result will be 0, this result would be -1. So at 0, the result is negative, and we have v of x is above 0. So simply, we can say near 0, it's asymptotically stable. Now let's go to 1 and -1. If we substitute it by a value of 1, here it will be 1. 1 minus 1 here will be 0. So at 1, the result will be 0. What about more than 1 and less than 1? Because we need all of the values. More than 1, let's say 4. So 4 squared, it will be here positive. 4 squared minus 1, the result will be positive. So for all of the values that's above 1, the result is positive. So v bar of x will be above 0. What about below 1? Below 1, we have, let's say, 0.5. So 0.5 squared will be negative 0.5 squared will be positive. -5 squared will be positive, but it's below 1 or less than 1. So the result will be positive multiplied by negative. The result will be negative. So now we have conditions. At 1, it's 0. More than 1, it's positive. Less than 1 is negative. So when you find a combination like that, then your equilibrium point will be unstable, because we mentioned that to make it asymptotically or Lyapunov stable, then the bar of x should be below 0 for all of the points, regardless the equilibrium point. So now we have 2 points. One is stable and another is unstable. The key takeaway for the Lyapunov functions is that Lyapunov functions provide a flexible framework for analyzing stability, especially when analytical solutions are unavailable, and these techniques are used in bioengineering to ensure robustness and reliability of the biological models. The third technique is called basin of attraction, and here we are getting a set of initial conditions from which trajectories converge to a particular stable equilibrium or attractor. Basin of attraction defines the region of influence for a stable state, providing insight into the robustness of the equilibrium. Why is this method important? Because it determines the range of perturbations a system can tolerate without transitioning to a different state, and it helps identify tipping points where small changes in the initial conditions lead to different outcomes. And it's critical in multiple applications such as cell-fate decisions, where the basin size determines the likelihood of differentiation pathways. There are multiple methods to determine basins of attraction, such as numerical simulations, where we are going to trace trajectories from various initial conditions to identify regions converging to the same attractor. Phase plane analysis for two-dimensional systems visualize trajectories in the phase plane to estimate basins of attractions. Lyapunov functions use v of x to determine boundaries of basin by identifying regions where v of x decreases. Also, basin of attraction encounters two challenges. In high-dimensional or chaotic systems, basin of attraction can have vector-like boundaries, making them difficult to compute, and small perturbations near the boundary can lead to transitions between attractors, and this highlights the sensitivity to the given initial conditions. To understand and get familiar with this technique, let's introduce this example. Let's consider this one-dimensional differential equation, -x multiplied by x minus 1 multiplied by x plus 1. And as you see, we can simply determine the equilibrium points by substituting here 0. So you have x with 0, x with 1, x with -1. So we have 3 equilibrium points. Next, we are going to analyze the stability of the equilibrium points. Let's say we are going to use a linear stability approach. So apply the Jacobian to the function, then substitute in the Jacobian or the output of the derivative to check and evaluate each equilibrium point. So for simplicity, multiply all of them together. You will get x squared minus 1 multiplied by x. So you will get -x cubic plus x. The derivative of it will be -3x squared plus 1. Substitute with -1. So you will get -3 multiplied by -1 squared plus 1. You will get -3 plus 1. You will get -2. It's negative. This means this equilibrium point is stable. At 0, this will be 0 plus 1 will be 1. Positive, this means unstable. At 1, 1 multiplied by -3 plus 1 will be -2. It's negative, so it will be stable. Now we have 2 stable points and 1 unstable point. Then we need to determine the basins of attraction. So this step comes after getting which is stable and which is unstable. So the unstable equilibrium here acts as a boundary between the basins of attraction of two stable equilibria, x -1 and x is 1, because if you plot them, 0 is here, 1 is here, -1 is here. So these are attractors, and this can be considered as a boundary between them. So if you are going to plot them, as we are going to do now, you will find that the points will be attracted to -1 if you are dealing with that region, and other points will be attracted to the other attractor, which is 1 if you are dealing with that region. So as you notice here, let's say we have 3 initial conditions or 3 points here, -2.5 and +2.5 and 0, as you see in the legend here. As you see, by increasing the value of x, or over time, it will be attracted to -1, which is here, and here will be attracted to 1, which is here. And at 0, if you are getting any value around 0 here, the trajectory neither move toward or away from it, because it's unstable equilibrium. And if you notice here, the arrows are starting to approach, and then they are going to diverge here and here. This is output from Bison plot, and this will be the output for MATLAB plot. And now we will know how to plot both of them using Python and MATLAB. Now go to script lecture 9, lab exercise 1 phase. Here we imported the necessary libraries. Then we created the system with the same given equation, and it's 1D system. We defined another function called system2D, and it's for the second example that we are going to cover after a while. So let's ignore this function for now. Here we created a grid of initial conditions from -15 to 15 with number of points equals 50. Then to draw the arrows, we created the vector field, and we used the quiver function from the plot to plot the vector field. And to do that, simply we created the velocity component u and looped at each point to get the corresponding value from the system 1D and appended it to the u vector. Based on that, we got the magnitude to apply normalization. And here we apply normalization by dividing u over the magnitude, and this will be our horizontal component, and the vertical component will be 1 over the magnitude. Using these two components, we can now plot the quiver plot. If you don't need to apply that to get the arrows and only need to check the trajectories, then simply apply initial conditions and set a time span so that you can know the trajectory or the behavior of the trajectory, get points for the time, and for each initial condition, solve the system, and then plot it, and also plot the starting point as a star symbol. So it's very simple. Getting initial conditions, solve the equation, which is system 1D, and get the trajectory and plot it to get that diagram for that point, and that point, just in case if you don't need to plot the arrows here. And for MATLAB, we did the same for u and v, and use the same function, quiver, to plot the phase portrait for 1D system. Also set the conditions, set the time span and the time slot. Here also solve the equation using the ODE 45 function for the system 1D, which is defined at the bottom, and plot that. Also don't forget hold on and hold off. And for the system 1D, here we are defining the function in our example, and this will be the corresponding output for the 3 points. You can update the system to another 1D system and solve it using handy calculations and validate it using the code output. Now let's go to another example for a 2D or two-dimensional system. First, we played with a one-dimensional system and got the output. Now we need to handle a two-dimensional system. We have the Lotka-Volterra equations, dx by dt equals alpha x minus beta xy, and the second one, dy by dt, is negative gamma y plus delta xy, where x of t is the population of prey and y of t is the population of the predators. Alpha is the growth rate of prey in the absence of predators. Beta is the rate of which prey are consumed by predators. Gamma is the death rate of predators in the absence of prey. Delta is the rate of which predators grow due to consuming prey. And this system models a cyclic interactions between predators and prey's populations. Our aim to apply the basin of attraction. So here, let's use the linear stability again for that example. And if you notice, we have two-dimensional systems. So how to deal with this using linear stability analysis to find the equilibrium points and if they are stable or not? Simply apply each of them to 0 and find the corresponding points. How? Simply, we have this equation, factor out x, you will get x multiplied by z1. Here, for the second equation, factor out y, it will be y multiplied by z1. Now we have x equals 0, x, and from z1, y will be alpha over beta, and from here, y will be 0, and from here, x will be gamma over delta. X refers to the brace. So if x is 0, this means no brace exists. And if y is 0, this means no predators exist. And if x and y have values, this means that the predators and the prey population has a balance. So now we have two equilibrium points, one at 0 and 0. This means that extension of both populations, and another one at zx and zy. And this means the coexistence of predators and the prey. We have two-dimensional systems, two equations and two variables. We will use Jacobian 2 by 2. The first will be the first equation, as you see here. The second row will be the second equation, as you see here. The first column will be according to x, and the second column is according to the derivative of y. Apply the derivatives here according to x. It will be alpha minus beta y here. From here, according to y, this will be ignored. Here it will be negative beta x. From here, this will be cancelled. So here will be delta y. And from here, according to y, it will be negative gamma plus delta x, which is here. Now we have the Jacobian. From the Jacobian, and each point find the eigenvalues and then check if they are stable or not. To apply the eigenvalues, simply multiply by, add this part, negative lambda multiplied by the I matrix. And the I matrix here is by setting all fields by 0 other than the diagonal, and the diagonal will be 1s. So here, alpha minus lambda multiplied by 1, so alpha minus lambda 0 minus lambda 0 will be 0, 0 minus lambda 0 will be 0, minus gamma minus lambda multiplied by 1 would be minus lambda and minus gamma. Get the determinant, multiply that minus multiply that, so it would be that equation. From here, we have two factors, z1 and z1. From here, we have alpha minus lambda, so lambda will be alpha, so alpha is above 0. And from here, minus gamma minus lambda, so lambda will be minus gamma, so it will be below 0. As we have one eigenvalue is positive, then this point will be unstable. As we mentioned, that if any of the points or any of the parts is above 0, this means it's unstable. Let's check the second point. So substitute with that point in the Jacobian, you will get that matrix. Now get the eigenvalues. Do the same from here to here and find the values. Apply the determinant, so minus lambda squared minus that factor by that factor. So you will finalize all of that and simplify to get lambda squared plus alpha multiplied by gamma equals 0. So this will be moved to the right hand side with a negative sign. So now we have an imaginary point. So it's pure imaginary because we don't have any real part. So at this point, we have a periodic behavior around this point, and we can say this point is not stable or not unstable. It's neutral stable. So when you find something like that with an imaginary part or pure imaginary part, then the system accepts periodic behavior around this point. And periodic behavior means that the system continues to loop or there are cycles around that point. So the system has a point which is unstable and another point with cycles. And if you are going to plot it using these 2 points, you will find the following output. At this point, they are diverging and deviating from the point, as you see in the arrows here. And around this point, there are multiple cycles. And for each, we are changing the initial conditions and getting the behavior. As you see in that behavior, they are applying cycles around that point. And the same for MATLAB. This point is 0, and this point is our second point. And these are the cycles around it, regardless the initial conditions. From the same code, we apply the same thing, but here we created the system 2D, created the two equations, returned both of them together, and at the end or the second part of the code, we first created XY values and created a mesh grid, defined the values for alpha, beta, gamma, and delta. They are called parameters. Created the U and V vectors, horizontal and vertical, or the velocity components, using the same approach. Now we have U and V. We can use the stream plot to plot something like a stream, like that, ours, like that stream, or you can use the quiver function to plot the vector field. Using this or that, you will know the directions, or whether it's converging or making cycles, or converging or diverging, and so on. Also, you can add a trajectory if you want, set initial conditions, the time, and for each initial condition, get a solution, plot the trajectory. You can plot the start point and end point, and to check at which point they are starting and at which point they are ending, and the ending point depends mainly on the time. It will apply for each of them for the initial conditions, and as you see here, the starting point is from here for that initial condition, and the ending point will be on the same trajectory. This is another starting point, and this is the same point after ending, and as you see, they are looping in like a circle or periodic behavior around the point without any convergence or divergence. The same for MATLAB, we defined the system 2D, two equations, and here we define the same parameters, calculated U and V, the velocity components, and then plotted using the quiver function. Also here, we plotted the trajectories using the ODE45 function, plotted the trajectory with the starting and ending points, as we did in Python, and this is a corresponding output, and both of them has a periodic behavior for the initial conditions using these parameters. So the key takeaway from the basin of attraction approach, it's crucial and a critical concept for understanding the robustness and reachability of stable state in nonlinear systems. It bridges theoretical analysis with practical applications in bioengineering, and this enables the design of reliable and resilient biological systems. So in this lecture, we have introduced three techniques: the linear stability and the Lyapunov functions and basin of attraction. And we can say that you can use the three methods to gain a general and global insight overall the system. Also, you can apply the three techniques to linear and nonlinear systems, and especially in nonlinear systems, as in linear systems, we can simply solve them analytically and gain insights using their plots, as we discussed earlier in the previous lectures. In the first method, we require the Jacobian, and based on the Jacobian, we determine a coordinate if it's more than or equal 0 or below 0, whether it's stable or not. And for the second method, Lyapunov, we are suggesting a function, and based on the signs of the function and the signs of its derivative, we can determine if it's Lyapunov stability, asymptotic stability. And for the last one, basin of attraction, we are getting the help of the other two techniques, Lyapunov and linear stability, to get the stable and unstable points. And based on that, we needed to find the space or the shape of the phase plot or the quiver plot, which is a vector field. And according to it, we are checking the behavior, whether it's diverging or converging or making a periodic cycles, as we saw in the examples. By combining these tools in our toolkit, we can be able to design reliable biological systems.